Welcome to Module 203F on cooling systems. Now, if you live in the Medicine Hat area, you know the importance of a good cooling system, and it is an integral part of the heating system. This module has three different objectives that we're going to go through. First, we're going to look at the individual components that make up a cooling system and what their jobs are. And then we're going to look at the operation of a typical cooling system. And lastly, we're going to look at the requirements of putting a cooling system into an existing forced air heating system. Let's look at the components that are used inside a typical system. The electrical side of an air conditioner unit is fairly straightforward. However, it is the understanding how the units work that will allow us to troubleshoot the units when it's necessary. And it's all based on a very simple physics principle. Gases and liquids will get hotter when they're compressed, and the same gases and liquids will lose heat when the pressure decreases. The cooling system consists of two main parts that allow for heat transfer. First, we have an evaporator coil, which absorbs heat from the circulating house air, and then we have the condensing unit that gives its heat up to the outside air. In a standalone unit, such as a window-mounted or rooftop-mounted unit, both of these two components are in the same part. However, in a forced air heating system, then they are in two different locations. The evaporator coil would be found in the upper part of your furnace, and the condensing unit would be a separate unit on the outside of your house. Either way, the refrigeration cycle is the same for both these different types of units. The condensing unit itself also consists of two primary components, the first one being the compressor. The compressor is hermetically sealed and has a driving motor inside it, and it compresses the refrigerant. The input to the compressor is cool, low-pressure vapor, and then it condenses it into a hot, high-pressure vapor on the other side. The other part of the condenser unit is the condenser coils. These are finned radiator that is cooled by air passing through, and it is located where the heat is to be discarded, typically outdoors. The compressor will feed the hot vapor into the coils, and then the vapor cools inside the condenser into a liquid state. However, it is still under pressure. The high pressure cooled liquid from the condenser coil enters into the refrigerant control valve, which is a thermostatic expansion valve. It uses a temperature sensing capillary tube and a bulb or a thermistor in order to control how much fluid goes into the control valve. And this controls the amount of refrigerator going into the evaporator coil. The refrigerant is a liquid that easily changes from liquid to vapor and back again. Typically, we would use Freon or chlorofluorocarbon gases, or CFCs. Keep in mind these are both bad for the environment, so it is illegal to let them disperse into the air. The refrigerant will have a pressure change happen inside the valve. If the high pressure warm refrigerant goes in from the condenser coil and the low pressure cold refrigerant leaves to the evaporator coil, and the pressure change is a result of the change in pipe size. Cool, low-pressure liquid leaving the control valve goes to the evaporator, which is a finned heat absorber mounted in the furnace plenum. The cool, low-pressure refrigerant is cycled through the evaporator coil, and then warm house air is pulled through the evaporator. The evaporating refrigerant absorbs the heat, leaving the air around it much cooler. And now, low-pressure cool liquid becomes warm, low-pressure vapor, which returns to the compressor. Next, we have some auxiliary devices that are also found on typical air conditioning units. We have the filter dryer, which is a combined unit that removes small particles and also removes any unwanted moisture. Next, we have a pressure control, which is a high pressure sensor connected to the discharge side of the compressor, and a low pressure sensor connected to the input side of the compressor. We also have an internal temperature sensor, which is a high temperature sensor that will shut down the system if the compressor overheats. And we have a low temperature sensor. The low temperature sensor shuts the system down if it is too cold outside, so the ambient temperature is lower than the evaporator temperature. We have short cycling protection, which stops frequent stop-starts in the system and also protects the system from starting when the pressure is too high. And lastly, we have the crankcase heater, which is only found in some systems. Its job is to keep the compressor crankcase heated so the refrigerant will stay a vapor, and it keeps the refrigerant out of the oil. Now that we're familiar with the components of a cooling system, we're going to see how they all work together in order to achieve the cooling that we need. The challenge to refrigerating air is how to take a room temperature vapor and make it so cold that it sucks all the heat out of the air around it. There are many changes that need to happen to the refrigerant in order to accomplish this. We need to change the temperature from hot to cool to cold and then back to warm. We need to change the state from liquid to vapor and back again, and we also need to change the pressure from high and then back down to low again. Each step in the cycle requires the refrigerant to meet different conditions. The physics principle that this system relies on is that evaporating liquid will draw heat from its surroundings, and the mechanical cooling system controls that evaporation, and it all starts with the compressor. Inside the compressor, we have warm, low-pressure vapor that comes into it from our house. The compressor's job is therefore to increase the pressure of that vapor. As the pressure increases, we are jamming more of the refrigerant into the same space, which creates more molecular friction, which creates a lot of heat. Anytime that we add pressure, we also add heat. The result is we have a high temperature, high pressure vapor output. So the compressor is responsible for two things. It changes the refrigerant from a low to high pressure, and in doing so, it also changes the refrigerant from a low to a high temperature. However, the state of the refrigerant stays as a vapor. The next step is to take that hot, high pressure vapor that comes out of the compressor and start putting it into the condensing coil. The coil has a fan which helps the hot vapor shed the heat to the surrounding air. The refrigerant is going to change its state as it goes through the condensing coil. As it loses its heat, it turns from a vapor down into a liquid. The result is that my output is now a warm, high pressure liquid. So the condensing coil is responsible for two things. It changes it from a hot to warm temperature, so it cools it down, and changes the state from a vapor to a liquid. But the pressure inside the condensing coil is going to be the exact same pressure as it was when it came out of the compressor. The next step is having that warm, high-pressure liquid going from the condensing coil into the expansion valve. And the amount of refrigerant that is in the expansion valve is controlled by the temperature of the evaporator coil input. This makes sure that the system doesn't freeze. The expansion valve changes the pressure inside by changing the size of the tubing between the input and the output. And now the high-pressure liquid being released into a low-pressure environment will significantly lower its temperature, and the temperature drop is approximate to the temperature rise that we saw inside the compressor. This results in an output that is a cold, low-pressure liquid, so the expansion valve is responsible for two things. It changes the refrigerant from a high pressure to low pressure, and that results in changing from a warm to a cold temperature, but it stays in the liquid state. Lastly, the refrigerant goes into the evaporator coil. This is placed in the upper air plenum of the furnace, and the furnace fan is interlocked with the air conditioning unit to circulate the house air through the evaporator coil. The cold liquid refrigerant from the expansion valve enters the evaporator coil, and since the refrigerant is so much colder, it pulls a lot of heat from the surrounding air. The house air enters the plenum warm, but leaves the plenum cold. As heat is being transferred from the air to the refrigerant, it changes state from a liquid back to a vapor again. This refrigerant typically has a very low boiling point. After the evaporator coil, now the refrigerant makes its way back to my compressor, which starts the cycle all over again. All four of my primary components are responsible for two changes to the refrigerant. Make sure you are familiar with what changes happen at which component, and also know what to expect for the input and the output of each component as well. When it comes to the electrical side of an air cooling unit, we can look at the schematic diagram for a rooftop unit. On here we can see both the low voltage control circuit as well as the power circuit. In the low voltage control circuit on the bottom of the screen, we can see the three different points of our thermostat being R, G, and Y. R is our source, G is our fan, Y is our cooling. We also see the thermostat contact that is going to be automated depending on the temperature of the room. There's also a high pressure and low pressure switch that are in line with the contactor. And when we have a call for cooling, we have the switch closed on the R, the thermostat will close, and that will activate both the indoor fan relay as well as go through the high and low pressure switch to turn on the contactor. On my power side, my contactor is going to control my compressor as well as my condenser fan motor out inside my unit. And I will have a set of contacts on both the line 1 and the line 2 side. We also have a control from the indoor fan relay to control the indoor fan motor, which would be our furnace motor. This way, when the system calls for cool, I have two relays that engage. I have the contactor relay, and I also have the indoor fan relay. The indoor fan relay will control my indoor fan, my contactor relay will control my compressor, and the fan outside inside the air conditioner unit. Due to the compressor and the motor that's inside it, we need to consider motor code rules as well. Rule 28604 Subrule 5 states that we need to have the disconnecting means for the air conditioning equipment within sight and within 3 meters of the equipment. But also keep in mind, if you place the disconnect directly behind where the air conditioner is going, it may not be accessible. So make sure that you place it in a smart location that you want to work on it. 28200 states that we must have its own branch circuit for the air conditioner, so it cannot share a circuit with anything else. And 28106 states what the wire size for it shall be, which is not less than 125% of the full load current rating of the motor. The purpose of this is because we have what's called an inrush current when that motor starts, so our conductor must be able to handle that. For our low voltage wiring, it should be 18 gauge, but that is up to a maximum of 35 meters. If we go longer than 35 meters, we have to upsize our gauge for our control wiring to 16 gauge because of voltage drop that's associated with the distance. When it comes to retrofitting an existing heating system with a cooling system, there's a few things that need to be added and a few things that need to be changed out. On the mechanical side of things, we need to add the cooling unit to the outside of the house, as well as adding the evaporator coil inside the plenum itself. We also need to make sure that the furnace blower fan is a 2-speed blower fan because we require that high speed for the cooling. Electrically speaking, we need to change the thermostat over to a heating and cooling stat, which requires an extra wire for the terminal on that thermostat. We also need to make sure that we have an indoor fan relay that could be placed on the circuit board on newer furnaces, and this turns the blower fan from low speed to high speed. It will have a normally open and a normally closed contact. We might also need to check the transformer to make sure that the VA rating is good enough for the extra load of running the controls for the air conditioner. We require line voltage wiring for the compressor unit, and we need low voltage wiring from the furnace to the power relay inside the compressor unit as well. In order to complete the low voltage wiring, you need to connect a wire from the Y terminal on the thermostat to the Y terminal on the furnace. You also connect a wire from the Y and the C terminal on the furnace and to the power relay coil in the air conditioning unit. The high pressure and the low pressure switches are integral to the AC unit. However, the outdoor thermal switch should be installed in series with the power relay coil as well. If a fan relay is needed for an older furnace unit, then it should be wired in parallel with the power relay coil. Once the system is properly installed and wired, you may have to deal with troubleshooting, and troubleshooting can be broken down into either electrical problems or mechanical problems. With electrical problems, we have to look at both our power circuit and our control circuit. The power circuit is fairly simple and is the easiest one to check. First, double check the breaker and make sure that's on. If the breaker is tripped, there's a reason why it tripped and you should find the reason before resetting it. It could be that the motor and either the compressor or the fan is seized inside the air conditioning unit. Make sure you resolve that problem and then reset the breaker. Go outside to the air conditioning unit and check to see if you have the proper line voltage going into the input of the power relay inside the air conditioner. If you don't have voltage there, it could be the disconnect is off. If you do have proper voltage there, check to make sure that both the compressor and the fan unit are in proper working order by visual inspection. If everything looks okay, you can push down the manual override on the power relay to see if the air conditioning unit fires up. If it fires up, then you know that the power circuit is fine. If the compressor doesn't fire, then there could be a problem with the seized compressor. If the fan doesn't run, then there could be a problem with the fan. If everything works, you can move on to the control circuit. When diagnosing the control circuit, always check to see if you have voltage first. Either check the transformer or check the electronic circuit board to make sure you have 24 volts between the R and the C contact. If you don't have that voltage, then we know that there's a problem with the supply voltage for the control circuit. If you do have voltage between the R and the C, the next thing to check is by turning on the thermostat to cool and turning down the thermostat in order to close the cool switch. Then go outside and see if you have 24 volts coming up to the power relay. If you have 24 volts across the coil of the power relay, then that should tell you everything should be working, but there's going to be a problem with the power relay unit itself, and that needs to be changed. If you do not have voltage at the power relay, then step backward from there, working your way back towards the thermostat. Check the outdoor switch. If the outdoor switch is open, you should have 24 volts between the common and the input side of that switch. However, you will not have anything coming out of it. And that would indicate if it's too cold outside, that switch is likely to be open. However, if it is warm outside, that switch needs to be changed. If the switch is okay, but you're not getting any voltage coming out to the switch, then once again, we need to look at the thermostat. It's possible that something could be wrong there. Go back down to the furnace and check between the Y and the C on the furnace circuit board. If you have 24 volts between the Y and the C, that would indicate that you have a broken wire or a bad connection somewhere between the furnace and the air conditioner. If you do not have voltage between the Y and the C, then the problem is likely going to be at the thermostat, and that's going to be your next stop. Go up to the thermostat and remove the cover and check the voltage between the Y and C on the thermostat. If you have your voltage there, that indicates either a bad wire or bad connection between the thermostat and the furnace. However, if you do not have that, it might be a bad thermostat itself. But make sure you have voltage coming into the R and C terminal at the thermostat. Just by following our schematic diagrams through, we can check each and every component, and we should know whether or not we are going to have line voltage or control voltage at every spot. And if we don't, we have to determine whether or not that is correct or incorrect, and if it is incorrect, that will indicate our problem. Before you continue on, make sure you really understand the principles behind how an air conditioner can cool a house, because our next topic, being a heat pump, uses the exact same principles, just in a reverse direction. A heat pump is an AC system that can deliver either heating or cooling, and it reverses the refrigerant flow for heating, so the outdoor coil will become the evaporator, and the indoor coil now becomes the condenser. It will require a four-way reversing valve in order to control the refrigerant direction to switch between the heating mode and the cooling mode. Some of the main components that we see in air conditioners, such as the outdoor coil, the indoor coil, and the compressor and the expansion valve. We also have that extra four-way reversing valve to change the direction of the flow of the refrigerant. We also need to have a double active thermostat to control both heating and cooling, a sequence timer to make sure everything is working in the proper order, and a defrost timer just in case things do freeze up. Some of the limitations that we have with a heat pump system is that they don't always work in areas with extreme cold weather. -20, it will still work. However, -30 to -40, we might need to have auxiliary heat. So if we don't pull enough heat from the outside air in order to utilize it inside, we could have electric baseboard heaters or even a gas appliance in order to help with the airflow inside our house. When we look at the operation of a heat pump in heating mode, we find that the compressor is still changing the pressure of the refrigerant. However, as the pressure changes and it builds heat, instead of pumping that heat outside, it's actually pumping it to the air exchanger on the inside. So the indoor air exchanger becomes our condenser. The hot refrigerant will go through transferring its heat to the inside air, and as it cools off, it will then transfer itself over to the expansion valve. The expansion valve also facilitates a change in pressure, which will cool the liquid significantly and pump the cool liquid outside. As long as the cool refrigerant is lower in temperature than the outside air, there will still be heat transfer from the outside air to the cool refrigerant. So even if it's minus 20 out, I could still warm my refrigerant as it goes through the outside coil. So as it goes through the outside coil and it becomes a gas again or vapor, it will return to the compressor and the whole system starts over again. In order to change this from a heating cycle to a cooling cycle, we can change our reversing valve, which will change the direction of the refrigerant and allowing my outdoor coil to become my condensing coil, and now my indoor coil becomes my evaporator coil again. You've now reached the end of Module 203F. Return to Blackboard and do the knowledge check and continue on to 203G.